Welcome to part 2 of me discussing the MOSFET datasheet and its characteristics. So if you haven't seen part 1, I suggest you do that, because this is going to go further into what we discussed before. What we exactly discussed before were the characteristics, and now we are going to take a look at some of the graphing. So let's get to it. First thing is figure 1, which is the typical output characteristics, and what that is the drain current, so the input current of the MOSFET versus the drain to source voltage. And each of this line, as you can see in this box over here, that is one of the lines. So starting at 2.5 volts is the bottom line, and the very top line is 15 volt VGS. If you remember, so let me draw the symbol. So we are looking at ID, which is the current that's coming into D, drain to source voltage, and VGS. Alright, so here we can see the operating parameters, such as a 20-second pulse width, microsecond pulse width, and a junction temperature of 25 degrees Celsius, which is just the startup, so when you just turn it on, and mostly it's room temperature, little bit higher. And so if we look at these lines over here, we can see we are starting from 0.1 volts VDS. That's not much. It means that if we look at this symbol, that we only have 0.1 volts. If this is tied to ground, then we have 0 volts over here, and then VDS is the input voltage. So let's assume that. So starting from 0.1, then this is 0.2, 0.3, 4, 5, 6, 7, 8, 9, 0.9, and then we get 1. Same over here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 10, 20, 30, 40, so forth, up till 100. And as you can see, it doesn't go further than this, which is about 10, 20, and this is 30, 25 volts. And if you look at the first line, which is at the gate to source, which is the gate is 2.5, and if you remember that V threshold was about 1 to 2 volts, so we are starting at 2.5 volts, and further we go into the drain to source voltage, the current doesn't really increase much. As you can see over here is a point which is 2, 3, 4, 5, 0.5 volts only, and all the way up to 25 volts. It doesn't change much. So that's important to know, that the gate voltage does indeed matter. You can just use any voltage. You must look at the datasheet for the optimal voltage. So if you go further, we see better results for higher voltages. This is, for example, 3 volts, and this is 4 volts, and this is then 6 volts. So as you can see, then comes 8 volts, and this whole section of lines all the way is 8 to 15 volts. So as you can see, that it delivers almost the same results at 8 volts as it does at 15 volts gate voltage. So that's interesting to know when you're using, for example, 12 volts as your maximum input voltage, that you don't need 15 volts, because here 12 volts is very close to 15 volts. And now we are going to look at figure 2, which is the same thing but for a different junction temperature. So this is when you're at maximum operating temperature with the same pulse width and the same scale, as you can see over here, and also the same VGS voltages. But what is different is these wave lines. For example, 2.5 now allows much higher current. You can draw it a little bit over like this. This little change over here, as you can see, draw a line. So as you can see, this little change at a higher operating temperature, and for the rest it's almost the same. This one is almost the same. This one has gone a bit down. It went from, this is 10, 20, 30, 40, almost 50 amps. And it came from 1, 2, 3, 4, also 50 amps. So maybe it's just my eyes, but it dipped a little, as you can see. And then this one, which is this 2.5, 3, 4, 6, and this was originally 6, which is also dipped a little, as you can see, from 150 amps to 100 amps, which is a lot less. Same goes for the other ones. and you see there's a little bit of gained VDS voltage, but if we can see is that it went a little from here to over here, meaning that the VDS voltage had to be increased. So the voltage at this point had to be increased to get the same about the same current, which is the reason it comes from the resistance increasing. And if we remember from Ohm's law, if the resistance goes up, the current goes down. So what you must do is you must increase the voltage as well, so this can be the same about. So that had to be done, which you must realize for this temperature is that the resistance goes up as well. So you must increase the voltage, which wasn't the case for this 2.5 volt. If I see correctly, this point and this point are about the same still, but this is for low current. As you can see, it's only at 3 amps, which shouldn't really matter much. But as you can approach higher currents, you can see it has a much greater impact. So I hope that was a little clear. If not, you can rewatch this part and try to figure out yourself. So next is the typical transfer characteristics, and it is displayed as the drain to source current versus the gate to source voltage. If I draw the symbol again, so we are looking again at drain current, and at this point so what we see here is VDS is 25 volts. So if this is ground, we apply a voltage of 25 volts, same pulse width, and what we see here is the two different junction temperatures. For this is the maximum rated junction temperature, this is about room temperature. So if we see here, we can see 3, 4, gate voltage up to 9, and over here we can see all the way above about 180 amp, but as you remember, this was rated for 45 amps, and perhaps it comes from the logic level. I'm not very sure about that, because this is this 10, 20, 30, 40, 45, and that's about here. If you take a look at this line, you can see it crosses these lines, so perhaps it has something to do with that. I'm not very sure. But if you take a look at these lines right now, so if we increase the gate voltage, we can see how it allows more current. For example, here if we apply 5 volts, we are at 100 amps and so forth. very clear to see different behavior at this temperature. But other than that, it's pretty much the same as before. Just look at what the lines do at your operating parameters and such. So this is what I was. So now we are going to take a look at figure 4, and it was what I was talking about. As the resistance goes up, when the temperature goes up, you can also see that kind of here as the current decreases at a higher temperature. So this is a pretty linear line, not very linear but still pretty linear. But what you can see here is the RDS on, so the resistance between the resistance as the MOSFET itself. So the resistance of the MOSFET itself when it's on, and the temperature of the junction. So as we can see over here, this is 175. Just probably breakdown temperature of the case itself. And here we are at minus 55 degrees, which is also in the data sheet, as I remember correctly. So this is our operating current. This is our gate to source voltage. So gate to source voltage at 10 is not even on here, but if you take a look at the previous one, perhaps it has more information. But as the temperature goes up, the resistance goes up, which is pretty self-explaining, I think. If you have any questions regarding it, then you can leave them, but I think it's pretty self-explaining. So now for the capacitances and the MOSFET. So I talked about them before, as you can see here in figure 5. You can see them back again, what they all mean. Where the input and the output and such. So if I draw this more visible, as you can see over here again, these are the capacitances at the MOSFET itself, which are these. So if we can see the capacitance in picofarad, and the drain to source voltage, this is 50 volts max, and here we are at 2400 picofarads with 2.4 nanofarads. This is from a very low voltage, and we can see how we start at almost 800 picofarads. And later I'm going to show you the problems that come with buying counterfeit MOSFETs from eBay and such. So take a close look at this graph. We first start with CRSS, which is only the gate drain capacitance, which is this one. This capacitance. as you increase drain to source voltage, the capacitance at gate to drain then decreases with this corresponding line, and this is pretty good to know for the gate capacitance you are going to use. For example, if you have 12 volts, you then look at about here, you see, okay, this is about 200, 400, 200, yes, 600, this is about 200 picofarads, and the C output capacitance, which is drain to source and gate to drain, which is these two, meaning this is the output, this is the output, so this must be the output, which is probably for electron flow. And if you take a look again what the output capacitance will be, it's about 550 picofarads. So then you have this here, and maybe it's pretty important, well, it is important to me because I'm going to work with the internal diode and the capacitance to first charge up the capacitance and then let the diode conduct at a certain voltage, which then creates a sort of voltage bridge between drain to source, and the voltage at the drain and the source should be equal. Therefore, if you switch it on, it's called zero voltage switching because there's no voltage difference. So that's pretty important to know this value for that case. And then the input, which is at the gate mostly, CISS, which is gate to source, gate to drain, and CDS is shorted, therefore this is bridged. And starting at a pretty high voltage capacitance at 1 volt, which then drops to 1600, still pretty high, 1.6 nanofarads, which is at a gate source voltage of 0 volts. And that's the input capacitance. And this, what's next is figure 6, which is important for the next episode, which is gate driving. So let's take a close look at that. Typical gate charge versus gate to source voltage. So what we can see here is the charge at the gate in nanocoulombs, and the gate to source voltage with the parameter of the drain current at 25 amps, and these different input variables as the drain to source. As you can see, there's a little bit of difference which you must keep in mind. Perhaps it's a little bit linear. Yes, it is linear. Therefore you can estimate, for example, 12 volts, that it's about like this. Let's say, for example. Maybe it's not so true, then you must create a test circuit, which we can see later. Here, test circuit. But let's take a look at the total gate charge nanocoulomb. If we increase the gate to source, here we can see the kind of 3.3 volt gap, which is kind of logic. And you see how from 3 to a little bit above 3, then the charge increases by a very big amount, and then it goes fully linear. So let's say we are at 9 volts, at 28 volts, we have 50 nanocoulombs, and then the current we require, let's say we want a rise time of 20 nanoseconds, we need a current of 2.5 amps, which is quite a lot. That's about it. It's not really much to it. I'm not sure what happens if you increase the current. I'm not sure if something is supposed to happen or it's supposed to be the same. But if it was really different, then they would include it. So I think you can assume the same for this current, but I'm not very sure about that. So let's take a look at the next couple of graphs. So next up is the figure 7, typical source to drain diode forward voltage. If I draw the symbol again, and they mean this diode from source to drain, which is then the source to drain diode, and it has a forward voltage of, let me check, it had a forward voltage of 1.3 volts, which is about here. And then this is reverse drain current, because normally current is like this. Then the reverse drain current is coming from this way. And in my application we have this drain to source capacitance. So we have a voltage over here which builds up to about volt, let's say 1.3 volts, and then this starts to conduct, and over here we have a transformer, let's say, which has a parallel resistance, which there is a voltage drop, and then this voltage over here gets kind of saved, well, it then goes from, if you watch my video about my plan on the gate, the capacitor charger I'm making, I explained with all 4 MOSFETs how the working principle is like. For example, the procedure of this capacitor then discharging through here, which then this becomes 0 volts, this becomes 0 volts, then we have 0 voltage switching. So let's take a look at the graph again at different temperatures with the VGS of 0 volts, therefore it's not on. And we are basically using the diode, the MOSFET as a diode alone. So we're starting here from about 0.85 to 0.9 volts, and here even less. And then we approach this is in 20, 30, 40 amps, all the way up to 100 amps. And then we approach the threshold about here, which is almost the same for both, so I don't have to worry about the different temperatures. And then the 25 degrees Celsius then goes a little above the current, goes a little above the 175 degrees line at a voltage of about 2.2 volts. So that's it's a pretty simple graph. Unlike this one, it looks a little much, but let's see if we can get out of it what it means. So let's take a look. What this says is maximum safe operation area with drain to source voltage on the x-axis and the drain current at the y-axis, and over here we can see different times, which is probably the pulse. Therefore what you can correlate this to is the switching frequency, which is 1 divided by the pulse time of the period. If you work with a duty cycle variable, for let's say, and they don't include the duty cycle because this is a single pulse, we can see also the different temperatures. Temperature case is 25 degrees and the junction temperature is 175. So if we take a look at this area, we have a pulse of 10 milliseconds, which is quite long. Therefore it is on for 10 milliseconds, and it's conducting that amount of current. So this entire area is safe operation for 10 milliseconds, because if you go above for 10 milliseconds, if you use a higher voltage, over here you get a higher current, and a higher current for this amount of time then can damage the MOSFET. And then we go up to a factor 10 less, so it's on for much less time, so we can again expand our area of safe operation. So now we can almost get over the 100 amps at only a voltage of 3 volts, because again this is pretty high, or this is pretty low, so this can go pretty high, which all depends on your resistance. So then again we decrease the pulse time and we have a even greater area where we can operate safely. This area that still is restricted because the current is too high for the voltage. For example, this over here, it won't do, because it probably will do, but it's not safe to do. And then we go even higher on the list by decreasing the pulse time, and this area over here is the operation is limited by the resistance, because as you can see it's a very low voltage, and if this is RDS on, then the current doesn't go above this line, which is a linear line. As you can see, this is also a linear. If this was a function, this would be linear. So as you can see, it's very dependent on your pulse times, what you can use as safety or not. If you take a look at 45, the 45 is about here. Which is the recommended operation current. And you can see how it varies also per switching time. For example, it is always, or not always, for the 10 milliseconds you can only get much higher than this, but if you go to a higher voltage it becomes restricted. This area then you can't use because of the high pulse time duration. So you must be aware that even if it says 45 amps max and you use it for continuous operation, that it might even fail because you are not inside the safe zone. So this is why higher frequencies are better for the MOSFET. So let's take a look at the next figure. So here's figure 9, which is the maximum drain current versus case temperature. And the drain current starts over here at a little bit above 45 amps at nominal voltage, nominal temperature, and then you see over here is a rapid decrease. This is all pretty linear, but then this goes very fast, and as you can see over here, 175C, the max current is 0, obviously, because if you draw current at the maximum temperature you get a breakdown and you might kill your MOSFET. It's pretty easy graph to visualize and to understand. So now figure 10. This is the switching time test circuit. This is a circuit where you can test your switching times. It's a very simple circuit. You simply add a waveform, in this case square wave, 5 volts, gate resistor, and then you add a probe, oscilloscope probe, at gate to source and drain to source. This is one probe which you attach, one here and ground of course, and one probe here also to ground. Very simple. A arbitrary drain resistor so that you don't short out the MOSFET, so you can analyze this waveform that comes out of it. So the first C is the drain to source voltage. If you turn on the MOSFET, here you turn it on, and you see this little delay over here. From here to here, which is the turn on delay, and this is the rise time. So this part over here is then, you then get this overlap, which means switching losses, because as this goes down you get a current flow from here to here, and as the gate approaches max you have maximum current flow, as you saw in the graphs earlier, for example. So let's say we have this, and then we still have this over here, but current starts to flow at much faster rate, which is at the threshold. The current starts to flow mostly. You can even see that in the graphs we talked about earlier. So then you have current, but you also have this voltage, and that means you have switching losses, which is not very great. So you must find a way to overcome these problems. For example, because this would be ideal that you just turn on gate, it turns on with it turns on instantly here, like this. Oh well, till you turn it off, which is over here. This would be of course ideal, and then the drain to source then drops from here and it goes like this. Or a little bit here. This would be ideal, for example, but it's not the case obviously, because nothing is ideal. So then we have this realistic graph, and of course at the turn off you have again switching losses with delays. Oh shit. So yeah, one solution is to firstly decrease the drain to source. For example, using this diode, you can have, if you have a high side, you have a load over here, then you have a voltage over here and a voltage over here. Or let's say we have a VDD voltage over here, and here we have 0 volts. Then we have a drain to source. But if we somehow get this VDD, then we have a voltage difference of 0 volts. And then when you accomplish that, you turn it on. For example, this is then your gate to source. And as you can see, this whole area is gone. No switching losses, and that's one way to approach 100% efficiency. Of course, you also have, this is not all, this is maybe conduction losses. If this is truly 0 volts, then you have this a little bit floating, which is just the voltage drop from the conduction. But ideally, this is what you want. And then over here, when it turns on, the voltage comes back, a drain to source, and this is when it's off. So don't get confused. This is almost 0 volts, and this is when it's on. Because the voltage you had here, now this is open, or well, this is closed, it can flow. So that should keep that in mind, that you don't think, oh, this is on because the voltage is higher. No, that's when it's off. So that's things to keep in mind when dealing with switching. If you want high efficiency, you should go this way, and this is 0 voltage switching. So as you can see, we are now at figure 13. It means I've skipped a couple of figures, simply because either I don't know too much about it, or it's not that important for basic operations. But this one is very important, which is the gate charge waveform. As you can see, here is the charge from gate to source, gate to drain, and this is the total charge of the gate. So as we can see over here, here's a little plateau, which is called the Miller plateau. And as we saw before, the gate to source, or well, the gate voltage looked linear like this. But as you can see, there's a little plateau over here, so this would be a better representation of, oh well, if I can draw it right. With these plateaus over here, that would be a realistic gate to source. Even if this is very small, it's still there a little bit. We're going to look at an example later where it's very visible and it can cause non-ZVS behavior. Therefore you have more efficiency losses because of this little dead time where it doesn't rise. Because if this was linear, you would just increase it like this, and then this is your maximum time, which is not the case. You have this distance in charge before it reaches the 5 volts instead of here where it reaches the 5 volts. So it's very important to keep in mind, and you can find these values in the datasheet to draw your own maximum gate charge requirements. And usually you can just take this, plug it into this and get your time. You can determine this or require this, what you need, for example. And this is the test circuit, which again here is a probe attached to here. You use these values in this arrangement. Little oscillator circuit. I'm not sure if it's oscillating circuit, but this is a constant current source with 3 milliamp current pulsed, and then you can determine the charge over here. As it is charging, you get the current, because if this is constant, then you can get this out of it, and you get the time, which is then represented as this will be time, and you can then calculate for these values. And now let's take a look at a experimental result of non-ZVS behavior due to the Miller plateau. As you can see over here, this is VGS and VDS. And as you can see, if it has a little dead time over here, which is this dead time over here, which is problematic because you have this overlap, and again you also have a current still. So what you must do is either get a dead time to shift this over to here, where it starts to rise like that, and you have no overlap. Either you can do that, or you must get rid of the plateau. And if I can find the result of that, I can. So what you then get is this, where no Miller plateau is visible, and you get the overlap is then removed. But as you also can see, is how did they fix it? Is they moved it to this division, which is the first, where it overlaps and it switches on over here, and it takes about one division to get over here. If you take a look at this one, it also starts over here, but this VDS is much quicker in falling, because it takes 2 divisions, and here it took about one. So you have more time for this to happen, because if if you use this same VDS over here, you still get 0 voltage switching. But here they also remove the plateau, as you can see, and you have perfect ZVS behavior, because there's almost 0 voltage at drain to source, and the current starts to rise a little bit over here, which is a very tiny bit of overlap, but it should not really matter. A little bit is it only, it's almost perfect. So that was that for ZVS behavior.